Assalamu alaikum everybody. This is the fourth lecture of the basic electronics course. I'm Dr. Saad Ahmad. Today we'll be discussing about the type of semiconductors which we have started in our previous lecture. Then we will talk about minority and majority carriers, and finally the current flow in semiconductors. We did the basics in the previous lecture, and now we are going to discuss these in detail. Okay, this was the periodic table we have seen in the previous lecture, and we have noted that we will be using group 3 and group 5 elements with group 4 elements to perform the doping process and create extrinsic semiconductor. So for the n-type semiconductor, we know that we need a pentavalent impurity, that is group 5, and from group 5 we have selected arsenic, and we will add pentavalent impurity to a pure semiconductor to get n-type semiconductor. Okay, so this n-type semiconductor will be produced by using the arsenic as an impurity atom, that is a pentavalent impurity. Okay, arsenic has 5 valence electrons, we know it, and fifth electron is superfluous, becomes the free electron and enters into a conduction band. Therefore the pentavalent impurity donates one electron and becomes donor. Hence pentavalent impurity is also known as donor impurity. Okay, we will look at the this is the structure which can be visualized when we use arsenic, shown here in the middle as the impurity atom, and the 4 silicon atoms on 4 sides of it. The blue electrons are belonging to the silicon atoms, and the black electrons are belongs to arsenic. But we know that arsenic has 5 electrons, so this is the fifth one I've shown here. This is the fifth one, and this fifth one is the one which is not bounded with any atom. Remember, when we have maximum of 8 electrons in the valence orbit, it becomes chemically stable and cannot increase its size. There are many chemical reasons for this. It is out of scope of this topic, so I'm not going to go into details about it. If you want, you can check out your chemistry. But for now here, what we get is that there is a vacant electron, a free electron here, and this free electron is not bonded with anyone, with any electron. So this is the one which can be dislodged easily, and when you show it in diagram, this is a silicon piece with 2 terminals, and if I have added 1 arsenic atom, then it's going to get you 1 free electron. If I add 2 arsenic atoms, 2 electrons, 3 electrons, 4 electrons, 5. In this way, manufacturers can control the number of free electrons in the n-type semiconductor during the doping process. You know that very well. When you are adding a pentavalent impurity, you are making a n-type semiconductor. So n-type semiconductor, and this is the diagram which we are going to use. If it is carrying 6 electrons, that means we have added 6 impurity atoms into the crystal structure. This crystal structure was discussed in the previous lecture. I hope you remember. So anyway, this is the diagram, and this is the process of doping, in which you have managed to create a free electron inside a pure semiconductor, and this pure semiconductor has now become a impure semiconductor, extrinsic semiconductor, a n-type semiconductor with free electrons inside it. Okay, okay, look at this. We have a central atom, an impurity atom coming from the trivalent group 3 element, that is boron, and the neighboring atoms are 4 silicon atoms. Okay, so look at this. We have 4 black electrons which are coming from the neighboring atoms, and boron, shown in red, have 3 valence electrons. Total atomic number is 5, so 3 valence electrons it has, and the fourth is the vacant area. This is the place which is vacant because there are only 4 neighboring atoms and 3 boron electrons, 4 neighboring electrons, and they are maximum 7. They can go for 8, but there are no more electrons to fill this space. So this becomes vacant. We consider it positive, we call it hole, and this is positively charged. And after the doping process, if you look at the figure of a p-type semiconductor, which is produced after adding a trivalent impurity like boron, and if you created one hole after doping, that means you have added one impurity atom. If you add 2, then it becomes 2, 3, 4, 5, 6, and so on. The number of plus signs shown in this semiconductor piece means that there are this many holes created, or this many impurity atoms have been added. So this is the two processes, one for creating n-type semiconductor and second for creating p-type. Okay, for p-type semiconductor we know that valence 3 valence electrons, and they are basically known as acceptor impurity. So whether you take boron or gallium, it's the same thing, because they belong to, they may have some different characteristic, but basic process is the same for both. Okay, in n-type semiconductors, the majority carriers are electrons, and the minority carriers are holes, the electrons and the holes in n-type semiconductor. Whereas in p-type semiconductor the case is opposite. The majority carriers are holes, because there are holes in p-type semiconductor, and occasionally you will find electrons there, and these electrons are minority carriers in case of p-type semiconductor. So this is not a very difficult thing to absorb. Anyway, this is the discussion for today. We'll continue it in the next lecture. If you have any questions, you can ask. Okay then, thank you very much, and Allah Hafiz.